Hello everyone. So this is the final lesson for the logarithm unit. This is lesson number 12 on instantaneous rates of change. If you haven't already, you should go through the lesson on average rates of change first, because that's kind of our introduction on rates of change. But I'm assuming you've already done that, so we'll start off on instantaneous rates of change. So instantaneous rate of change is calculating the rate of change now at a single point. Average rate of change was the rate of change between 2 points, the average amount that our y value is changing over that domain interval. Now we're looking at the rate of change at a single point, not over that lengthy interval. To find the steepness of the curve at a single point, we will find the slope of the tangent. So this is another difference. In average rate of change, we are looking at the secant, so a line drawn through 2 points on a curve. Now we're looking at a line that just touches the curve at one single point. Now, a lot of you who are taking calculus will have already talked about rates of change and likely derivatives. We're not using that method. This is assuming that you have not learned anything to do with calculus. We're going to use methods taught in this course to calculate rate of change. So I don't care if you know how to calculate derivatives. We're going to use the advanced functions method, which we'll get through in just a little bit. So in calculus, you will be able to do it exactly. For now, we're going to choose a very, very small interval in order to mimic the slope of the tangent at that point. So we're going to use two different methods. We'll use the difference quotient so that is, we're using our indicated point x, and we're using our second point is going to be x plus 0.01. That's the minimum accuracy we want. We can choose a point smaller than 0.01 to add if we would like, but that's the minimum accuracy we want, so the maximum distance of our interval. Or we can use a centered interval. So the centered interval, we're looking on either side of our intended value. So our first point will be x minus, again, the maximum we want to subtract. So our minimum accuracy is, we're going to subtract 0.01, and the maximum accuracy we're going to use, minimum accuracy we're going to use, so the maximum we're going to add is 0.01. So difference quotient, we're looking at our point and just above. Centered interval, we're looking just below and just above. So our x is going to be right smack dab in the middle of that interval. That's why it's called centered. To start off, we're going to look at our function on ice thickness that we had looked at in the average rate of change lesson. So that function is shown here on the whiteboard. We have our polynomial, so it was the function negative 0.1 d cubed plus 1.3 d squared minus 4.4 d plus 14.8. Gives us kind of this rough shape here. We'll bring this back in a moment. Let's write down our equation. T of d negative 0.1 d cubed plus 1.3 d squared minus 4.4 d plus 14.8. And so the question we're asked is, how is the thickness of ice changing at the 8th day of January? In the previous lesson, we were asked to look from or during the first 3 days. Now we're looking at one specific day. So we're going to do this with two methods. So first, we're going to use that difference quotient. So instantaneous rate of change, we're looking at the change of our function, the change of t of d divided by d, change in d. And so we're going to use our 2 points here. So in this case, our x is going to be 8, and our x plus 0.01 is 8.01. So this is going to mimic looking really close, or this is going to create a really small interval. So basically, it's going to give us that slope right at t of 8. So our goal here is we want to see right at t equals 8, what is the slope of the tangent, the line that just touches our function. This is our tangent, whereas before when we looked from 0 to 3, that's a secant. That's crossing our function at 2 different points. So this is for average rate of change. This is for instantaneous rate of change. So we're interested, what is t of 8.01? So we're going to plug that into our equation. So here's our first t of 8.01, and we're subtracting t of 8, we're subtracting minus 0.1 times 8 cubed plus 1.3 times 8 squared minus 4.4 times 8 plus 14.8, and so that is our whole numerator. I couldn't fit it on one line, and we're dividing all of that by 8.01 minus 8 is 0.01. So we'll start off, we'll see what is t of 8.01. So negative 0.1 times 8.01 cubed plus 1.3 times 8.01 squared minus 4.4 times 8.01 plus 14.8 gives us 11.5718899 minus our t of 8, negative 0.1 times 8 cubed plus 1.3 times 8 squared minus 4.4 times 8 plus 14.8 is 11.6. All that over 0.01. We've kept as many decimals here, so we have as accurate an answer as our calculator, or at least my calculator, will give us. And we're going to do that subtraction. and we get negative 0.028101 over 0.01, which will give us negative 2.81 approximately. So again, the top, our delta T, is ice thickness. This was given in centimeters. The bottom was delta D, or D was days. So this is negative 2.81 centimeters. Oh, let's try that again. Centimeters per day. So at the moment, because this is instantaneous, this is looking right at that moment of the 8th day. At the moment of the 8th day in January, the ice thickness is decreasing because it was less than 0, our rate of change, by 2.81 centimeters per day. So the slope of our tangent is negative 2.81. So that's using our difference quotient. We'll also look at our centered interval. And so in this case, we're looking our change of our function over our change in our independent variable. We're going to subtract our f of x plus our h. So again, we said that minimum accuracy had to be 0.01. So in general, that's what we're going to use. Sometimes we might need a smaller number for h, minus f of x minus h all over x plus h minus x minus h. So for this particular equation, our T of D equation, to find the rate of change, we're doing delta T of D over delta D. So again, we're going to use h equals 0.01. So we need to go 0.01 over the value we want to look at, so 8.01, and 0.01 less than that, so 7.99. And now our interval is centered around x equals 8, or d equals 8. We'll plug this into our equation. So negative 0.1 d cubed. So we're plugging in 8.01, negative 0.1 times 8.01 cubed plus 1.3 times 8.01 squared minus 4.4 times 8.01 plus 14.8. That's our first value, our t of 8.01, and we're subtracting negative 0.1 times 7.99 cubed plus 1.3 times 7.9 squared minus 4.4 times 7.99 plus 14.8. all of that, both lines there form our numerator. It's going to be over 8.01 minus 7.99 over 0.02. So we're going to calculate t of 8.01. We already did that in the last question. T of 8.01, oh, where'd we go? T of 8.01 was 11.571889. So we did that in the previous difference quotient. But we do need to see what is t of 7.99. So negative 0.01 times 7.99 cubed plus 1.3 times 7.99 squared minus 4.4 times 7.99 plus 14.8. Oh, put 0.01, should be 0.1. That gives us, so we're subtracting 11.627891. Again, we're going to use all the decimals for maximum accuracy. Divided by 0.02. Do our subtraction. Oh, 11.5718899 minus 11.6278901 is negative 0.0560002 all over 0.02 is approximately 2.8, negative 2.8. Again, T is ice thickness in centimeters. D is time in days. So this is negative 2.8 centimeters per day. So this method is telling us at the moment of the 8th day of January, the ice thickness is, we're still decreasing because we're negative, at a rate of 2.8 centimeters per day. So we get basically the same answer, 2.8. Last time we got 2.81. This method is considered to be more accurate. We're looking at both sides of the point that we're interested in. So the slope ends up more closely mimicking the slope of the true tangent. So the reason we don't always use this way is because we have to calculate 2 points with a decimal. Makes it a little bit more complicated. We just have both answers be these long decimals, but it is more accurate in general. So this is generally preferred. You may be asked either. Look at another example. The students in a laboratory company raise amoebas to sell to schools for use in a biology class. They predict the number of amoebas in a sample with the following formula. N of t equals 550 log base 10 of t. T is time in hours. And n is number of amoebas. Find the instantaneous rate of change. So we want the instantaneous rate of change at 12 hours. So instantaneous rate of change of this problem, we're looking at the change in n with regards to the change in t. We'll use our difference quotient for this one. So we'll look at n of 12 plus that h, 12 plus 0.01, 12.01 minus n of 12 over 12.01 minus 12. N of 12.01, we're plugging that in as t. So 550 log base 10 of 12.01 minus 550 log base 10 of 12 over 12.01 minus 12. $550 log base 10, so we don't need to put, we can just put that straight in. Log of 12.01 is 593.74865541 minus 550 log 12. 593.549683 over 0.01. 12.01 minus 12 is 0.01. We'll subtract our numerator. 3.74865541 minus 0.1989687772 over 0.01, and you get 19.897. N was the number of amoebas. Let's make sure I spell amoeba right. Bottom was our time in hours. So our rate of change, our instantaneous rate of change, is 19.897 amoebas per hour. So rate at the instant of 12 hours, exactly at 12 hours, the amoeba population was increasing. We have a positive rate of change at a rate of 19.897, about 20 amoebas per hour. One more problem. Back to talking about snowshoe hares. again, we're looking at this rational formula we looked at in the last lesson. P of t is 2550 t squared plus 1250 over 25 plus t squared. And the question asks, estimate the rate of change of the hare population 15 years after this park in the conservation area opened. So we want the instantaneous rate of change at 15 years. So the rate of change of our population with respect to time. P of 15.01 minus, we'll do the difference quotient again. P of 15 over 15.01 minus 15. So P of 15.01, 2550 times 15.01 squared, plus 1250 over 25 plus 15.01 squared minus P of 15, 2550 times 15 squared plus 1250 over 25 plus 15 squared, all over 15.01 minus 15, 0.01. So 2550 times 15.01 squared plus 1250 575,765.255 over 25 plus 15.01 squared, 250.3001 minus 2550 times 15 squared plus 1250, 575,000. So you can see how much of a difference that 0.01 really makes. It adds a whole 765 to this numerator. 25 plus 15 squared, 250. And we'll simplify our fractions. We get 2300.29974, 575,000 divided by 250, 2300. So 0.29974 divided by 0.01. We're going to get 29.974. Again, because these were approximate, these end up all being approximate. And we're looking at population of hares was our P. T was time in years. So at exactly 15 years after the park opened, the hare population we have a positive rate of change, so it's increasing. Increasing at a rate of 30 hares per year. And that's the end of this last lesson in the logarithm unit. So just those 2 lessons on rate of change, in addition to all the stuff on logarithms that we've talked about in the first 10 lessons. Next week, we're going to be focused on review of this unit, as well as an assignment. So keep asking questions you might have over anything from this unit. Enjoy your weekend, and you'll hear from me soon. Thanks for listening, and goodbye.